As of late, President Biden has introduced the primary picture to be shown unreservedly from the James Webb Telescope, the greatest and for the most part solid anytime sent off into space. The immensity of the tremendous web has done everything but baffle our journey for data in the field of cosmology. Furthermore, planetary assessments have compelled humankind to set up present-day space telescopes and send tests to explore the distant sublime characteristic. In this pursuit, we have uncovered new clear pictures of Proxima B and exoplanets moving in the gravitational embrace of Proxima Centauri. Its disclosure in 2016 opened new viewpoints in cosmic examination, and as of now, the most clear image of Proxima B delivered by the James Webb Telescope is here. It is a big deal. Epic. Stay with us to see the explanation why it is significant. Such a lot of Proxima Centauri is the closest known star to the Sun and was viewed as in 1915 by the Scottish space master Robert Innes. He perceived this red little star as the closest person from the Alpha Centauri star structure. 100 years sometime later, in 2016, an overall gathering of room specialists drove by Gon Onglat Escu found Proxima B, a magnificent body surrounding Proxima Centauri, organized inside the reasonable zone of its star. This exoplanet touched off energy on its disclosure, promising a normal impression into the cosmology of viable universes past our nearby planet bunch. Unveiled through the point of convergence of the James Webb Space Telescope, the meaning of Proxima B connects quite far past its heavenly presence, offering a tempting, amazing chance to explore the secrets of distant universes. The revelation of Proxima B was a defining moment in cosmology. Not enduring its closeness, innovative limitations had hindered clear examination until the new headway. Furnished with cutting-edge imaging and spectroscopic devices, the James Webb Space Telescope has now advertised cosmologists the absolute first direct image of this world-sized exoplanet. The image is a big deal. It has not previously expanded how we may decipher connecting heavenly bodies but also touched off huge consequences for logical examination beyond our nearby planet group. This image represents an essential achievement, offering a visual comprehension into an exoplanet staying within the bearable zone of a nearby star. This progression has filled energy inside standard scientists, restoring the journey to understand the likely validity of exoplanets and investigate the proclivities of life beyond our nearby planet group. So how was the James Webb Space Telescope, JWST, prepared to help us here? Arranged at the second range point, or L2, roughly 1.5 million kilometers or around 1 million miles from Earth, the JWST is the pinnacle of our space-age advancements. This location permits it to keep a consistent circle comparative with our planet as it spins around the Sun equipped with an assortment of cutting-edge logical instruments. The JWST can catch pictures and gather information across various frequencies, particularly in the infrared range. Its primary mirror is made out of 18 hexagonal segments and has a width of 6.5 meters or 21 feet. This is significantly larger than those of its ancestors. To picture exoplanets like Proxima B, the JWST utilizes its near-infrared camera, NIR-CAM, and near-infrared spectrometer, NIR-SPEC, among other instruments. The NIR-CAM is essential for imaging and distinguishing objects in the near-infrared range, while NIR-SPEC performs spectroscopy to examine the compound construction, temperature, and other properties of great bodies. Given Proxima B's separation from Earth and the difficulties of noticing exoplanets, the JWST's capacities are fundamental. Its infrared responsiveness permits it to recognize the weak infrared light transmitted by Proxima B, which is crucial for describing the planet, zeroing in on its environment, and perhaps distinguishing indications of tenability. The telescope's high goal and responsiveness empower it to assemble definite data about exoplanets like Proxima B, essentially adding to how we could decipher these faraway universes. The JWST was preceded by the Hubble Space Telescope, HST, which remains as a symbol in space investigation. Shipped off in 1990, the HST marked an immense leap in our understanding and cognizance of the universe. Its cycle follows back to the space race time of the 1950s and 1960s, a period described by intense rivalry between the US and the Soviet Association. This conflict extended past worldwide struggles and into the spaces of science and innovation, finishing in aggressive space programs. The origins of the Hubble can be traced to the outcome of the space race as space offices look to transcend the constraints of Earth's air, which distorts and impedes a large part of the approaching light from magnificent articles. NASA's response to the issue was straightforward. They imagined a space-based observatory that would sidestep these environmental limits and give outstanding clearness and exactness in astronomical observations. However, upon its farewell, an imperfection in the Hubble's essential reflect undermined its underlying capacities. The mirror experienced circular deviation, making pictures seem obscured. This reduced the telescope's impact and viability significantly and prompted a major re-examination of the undertaking and required a pivotal fix mission in 1993, where space explorers introduced restorative optics to fix the mirror's imperfection. Regardless of this early difficulty, the Hubble kept on upsetting our comprehension of the universe. It led broad reviews, including the Hubble Profound Field and the Ultra Profound Field, capturing pictures of amazingly far-off universes and revealing insight into the early universe's advancement. The HST also provided detailed pictures of planets within our nearby planet bunch, allowing scientists to study their airs, atmospheric conditions, and moons. The Hubble likewise observed heavenly birth processes and passings, revealing the mind-boggling subtleties of star-forming regions and planetary nebulae. Its observations added to estimating the pace of development of the universe, prompting the revelation of dark energy, a baffling power driving the universe's accelerated extension. However, while progressive, the Hubble had limitations. Its instruments, although notable at the time, relied on technology from the 1970s and 1980s. Moreover, its location in low Earth orbit didn't protect it completely from the planet's barometrical aggravations. Naturally, the need for a replacement, the James Webb Space Telescope, began from the desire to overcome these limits. The JWST was designed with larger and more advanced instruments, specifically optimized for infrared observations, enabling it to peer further into space, study the earliest systems, and describe exoplanets in ways the Hubble simply couldn't. The JWST thus represents a new era in space investigation, building upon the legacy of the Hubble while pushing the limits of how we could interpret the universe. The JWST has given us uncommon clearness in cosmology and the investigation of exoplanets like Proxima B. Proxima B's circle around its parent star, Proxima Centauri, is a spellbinding part of its qualities. Notwithstanding the relative proximity to the red small star, this exoplanet exists within the habitable zone, a region where conditions might permit the existence of liquid water. Its location in this zone doesn't reflect Earth's. However, Proxima B gets a fundamentally different energy intake compared to our planet. This variety in energy consumption strongly affects its environment, surface circumstances, and overall habitability. The potential effects of this energy change, whether it leads to extreme temperature changes or unique atmospheric structures, present interesting avenues for further exploration and understanding. Proxima B lives within enticing reach, at just 4.2 light-years away. Regardless of being Earth-sized and potentially habitable, it remained elusive because no telescope, ground-based or in space, has the ability to photograph this directly distant world. The JWST is designed explicitly for infrared observations and thus doesn't need to capture visually the planet. Instead, it focused on unambiguous infrared frequencies, following the variability of Proxima B as it orbited. This is a promising research area, and we have made many solid steps since the exoplanet's discovery in 2016. What truly distinguishes Proxima B is its short orbital period. The exoplanet completes a full revolution around Proxima Centauri in a mere 11.2 Earth days. This brief year raises compelling questions about the atmosphere and the potential habitability of the planet. Such a fast orbit suggests that Proxima B likely experiences gravitational and atmospheric forces entirely different from what we observe and feel here on Earth. These differences can shape its geology, weather patterns, and potential for holding an atmosphere. Clearly, there's much we want to learn about the planet. But how is it that we could think that it is in the ahead of everyone else? Embracing the intricacies of this adjoining exoplanet holds the commitment of uncovering insights into the broader questions of habitability and the prevalence of life beyond our solar system. Proxima B's location in its star's habitable zone has excited scientists, highlighting conditions favorable for liquid water, crucial for life. Regardless of the challenges presented by its proximity to its star, including extreme radiation, Recent JWST data suggests the presence of water vapor on the world, a crucial fact for habitability. Spectroscopic analysis offers insights into its air structure, helping in the quest for life-supporting components like oxygen and methane. These tools, combined with advanced atmospheric modeling, offer glimpses into the planet's climatic circumstances and help us formulate theories regarding its habitability. Further advancements in observational techniques and modeling will be instrumental in unraveling the mysteries of Proxima B's potential to harbor life. But the possibility of extraterrestrial life on the world, despite the challenges presented by the proximity of its star, is indeed worth entertaining. After all, we truly do have real-world instances of life flourishing in such challenges even back here on Earth. Extremophiles are incredible microorganisms that stretch the boundaries of where life can exist. They thrive in some of the most extreme circumstances on Earth, places that were once thought inhospitable, like extremely hot springs, deep-sea hydrothermal vents, acidic lakes, or freezing Antarctic ice. They have opened up additional possibilities for where life could exist, suggesting conditions previously deemed inhospitable could support life, just as the extreme conditions on Proxima B might be home to extremophiles. Earth has a diverse array of extremophiles, exhibiting life's versatility to extreme conditions. Among them, we have thermophiles that thrive in high-temperature conditions, like Thermus aquaticus, a bacterium thriving in hot springs, and Pyrococcus, found in deep-sea hydrothermal vents where temperatures exceed 100 degrees Celsius. Psychrophiles, on the other hand, thrive in freezing temperatures. For instance, Psychrobacter arcticus can survive in cold Antarctic conditions. Similarly, acidophiles like Acidithiobacillus ferrooxidans thrive in highly acidic conditions, while alkalophiles, such as Ponus flavus, survive in highly basic conditions. Ultimately, halophiles like Halobacterium salinarum live in highly saline conditions like salt pans, illustrating resilience to extreme salt concentrations. Considering the potential conditions on Proxima B, where extreme radiation due to proximity to its star might be a challenge, creatures like extremophiles on Earth could potentially adapt and even thrive. Deinococcus radiodurans, for example, boasts resistance to ionizing radiation, surviving doses thousands of times higher than what would be lethal to humans. Extremophiles have evolved various adaptation mechanisms, including DNA repair mechanisms, protective pigments, and unique cell structures. These adaptations suggest potential survival mechanisms that life forms on Proxima B could develop to thrive in its harsh conditions. Finding extremophile-like creatures on Proxima B, able to endure extreme radiation or other harsh environmental factors, would indeed change how we might interpret life's versatility beyond Earth. It could rethink the limits of habitability and expand the scope of exobiology, showing that life might thrive in seemingly hostile extraterrestrial conditions. However, this is easier said than done. Exploring Proxima B and other distant exoplanets present significant mechanical obstructions. Currently, we are facing limitations in directly observing and describing distant celestial bodies. While telescopes like the James Webb Space Telescope offer valuable insights, they have constraints in capturing detailed images or conducting close-up examination due to vast distances and the limits of available technology. Overcoming these obstacles requires advancements in telescope design, sensor technology, and perhaps even the development of revolutionary propulsion systems to enable interstellar missions. Future advancements for interstellar missions could revolutionize our ability to explore and understand exoplanets like Proxima B. Concepts including advanced propulsion systems like solar sail ion drives or even theoretical ideas like warp drives are under study. Now, these advancements aim to significantly reduce travel time to distant star systems, enabling closer observations and perhaps even direct examination of exoplanets. However, at this point, these ideas are mostly theoretical and require extensive research and development before becoming feasible for interstellar traveling. The exploration of Proxima B is critical for advancing our understanding of exoplanets and the potential for life beyond Earth. Studying this exoplanet and others within its habitable zone contributes vital data to refine how we might interpret planetary formation, habitability conditions, and the prevalence of life-supporting circumstances in the universe. Such data is crucial for future space exploration missions, guiding the selection of targets for further assessment and possible human colonization efforts. Proxima B is like a stepping stone toward unraveling the mysteries of distant worlds and expanding the horizon of our understanding of the universe. The study of exoplanets extends beyond Proxima B. Exoplanets are classified into various classes, including gas giants like hot Jupiters, rocky planets resembling Earth or Mars, and unique entities like super-Earths, each possessing unique qualities and potential for supporting different conditions for life. Advancements in exoplanetary research through telescopes like Kepler and the JWST have revealed the vast diversity of planetary systems in the universe, offering insights into exoplanet formation and potential habitability. These observations, including recent insights from the JWST, advance capabilities to shape how we might interpret exoplanets and guide future exploratory efforts. The JWST's remarkable discoveries extend beyond our nearby galactic neighborhood, with recent observations including the discovery of distant galaxies and the investigation of cosmic phenomena like star formation and black hole behavior. Its wide gaze has expanded our understanding of the early universe and opened new avenues of inquiry, fostering a deeper interest in cosmic complexity. The potential contributions from the JWST vow to revolutionize future galactic research with high-resolution imaging and infrared sensitivity poised to unveil the origins of galaxies and further illuminate the case for life's evolution. Furthermore, the possibility of encountering extraterrestrial life, potentially confirmed by discoveries like Proxima B, holds significant repercussions for how humankind could interpret life's existence and diversity in the universe, reshaping our perspective on our cosmic place. Finding life on Proxima B would drive advancements in various scientific fields like astrobiology and cosmology, prompting philosophical reflections about our cosmic place and ethical considerations. This mission could unite humanity, transcend cultural narratives, and fuel innovation in communication and technology while fostering global cooperation. It raises ethical dilemmas, yet signifies a grand transformation in human understanding, propelled by instruments like the James Webb Space Telescope, marking a new era of extraordinary exploration and reshaping our fascination for the universe.